So the next big idea that we want to add is electric potential energy. And if you think back to last semester, we saw that you calculate the work done by a constant force by thinking about the magnitude of the force times the magnitude of the displacement times the cosine of the angle between those two vectors. We also saw that you could define the change in a potential energy by thinking about negative the work done by conservative force. What we're going to do to think about the electric potential energy is we're going to put these two ideas together, and we're going to end up with an equation that tells us that the change in the electric potential energy in situations where you have a constant electric force is given by, well, change in the electric potential energy, that's the delta UE term on the left, equals plus or minus absolute value of Q times E, the magnitude of the electric field, times this delta D parallel. And that delta D parallel is just telling us the distance that your object is moving parallel to the electric field. And so if you think about this equation that's sitting here, if you look back up at that work equation in the top left, it says, hey, magnitude of a force. Well, we know that Q times E gives us the magnitude of the electric force. And then there's this R cosine phi term that's really sort of factoring into the plus or minus in this delta D parallel piece. In broad strokes, we can see sort of where all these details are coming from. Where we want to start is by thinking about this plus minus that's sitting out front. So the fundamental question that we want to start with is how can we determine whether the electric potential energy is increasing or decreasing? And so let's go back to a more fundamental question, which is how can we determine whether any potential energy is increasing or decreasing? Well, we dealt with two potential energies last semester, so let's talk about those two options. So the first one was the gravitational potential energy. We said, how can we determine whether the gravitational potential energy is increasing or decreasing? The fundamental question that we asked to sort of reframe that first one is the object moving up or down? And so if you remember, if you said, hey, there's an object, if it goes up, the gravitational potential energy increases. On the other hand, if that object moves down, then the gravitational potential energy is decreasing. The important idea here is that the gravitational force points down. So if you think about moving up and moving down, what that really is telling me about how I'm moving with or against the gravitational force. So another way to reframe thinking about whether the gravitational potential energy is increasing or decreasing, instead of thinking about is it moving up or moving down, is to say that the gravitational potential energy increases if the object moves against the gravitational force. And again, that's consistent with what we have over on the right. Object moves up, gravitational force points down. In moving up, it's going against the gravitational force, and we still get an increase in the gravitational potential energy. On the other hand, the gravitational potential energy decreases if the object moves with the gravitational force. So gravitational force points down, object moves down, gravitational potential energy is going to decrease. The second potential energy that we talked about was elastic potential energy. And again, we said if you want to figure out whether the elastic potential energy is increasing or decreasing, the question to ask yourself is the object moving towards or away from equilibrium? So we could start by saying, well, if the object is moving away from equilibrium, so again, the object gets pulled farther out from the equilibrium point, the elastic potential energy increases. On the other hand, if the object moves back towards equilibrium, then the elastic potential energy is going to decrease. Well, just like we did with the gravitational potential energy, let's think about what this really means in terms of the elastic force. And so we know that that spring force always points towards equilibrium. So we can reframe thinking about moving away from equilibrium as again saying that you're moving in the opposite direction as the way the spring force is trying to pull you, and so the elastic potential energy is increasing as you move against the spring force. On the other hand, if you're moving back towards equilibrium, you're moving with the spring force, and so the elastic potential energy decreases. So what you can see is, in terms of sort of generalizing this, how can we determine whether any potential energy is increasing or decreasing? Another way to think about this is the object moving with or against some conservative force? So the whole reason we kind of went through thinking about the potential energies we already know and giving ourselves a better framework was to come back and think about the electric potential energy. And so how can we determine whether the electric potential energy is increasing or decreasing? What we've determined is the fundamental question we want to ask is the object moving with or against the electric force? And again, just sort of as a picture, let's say I've got 2 point charges. They're both positively charged. That means we know that since they have the same charge, they want to repel each other. So the electric forces, right, the electric force that each charge feels points away from the other charge. If I force those charges to come together, I'm clearly moving them against the electric force, and therefore the electric potential energy will increase. On the other hand, if I let them move away from each other, now they're moving with the electric force, and the electric potential energy decreases. So what we can see is dealing with this plus minus is going to be relatively easy. All I need to know is which way does the electric force want to act on my charge, and usually that's simply a statement of saying, well, is it positively or negatively charged? What's the other charge around it? Which way is the other charge going to want to push it? I know which way the electric force points. And then if it's moving with that electric force, the electric potential energy will decrease, and I need a negative. On the other hand, if it's moving against the electric force, the electric potential energy will increase, and I'm going to need the positive sign. So that's the big idea. Fundamentally, the change in the electric potential energy of a charge as it moves in the presence of other charges indicates whether the charge is moving with or against the electric force acting on the charge. That's just sort of a fancy way of saying all in one sentence what we were just talking about before. It says the plus or minus comes from knowing whether your charge is moving with the electric force or against the electric force. And you can think about this as, again, we know from that equation on the top left, right, which is true for any conservative force, if we want to think about that just in terms of the electric force, it tells us that the change in the electric potential energy is equal to negative the work done by the electric force. And so if you think back a second ago to when those 2 positively charged particles moved away from each other, well, that's what they wanted to do, right? If you just let those 2 particles go, they're trying to repel each other, so they would have naturally separated. In that case, the electric force was pushing them apart. They moved with the electric force. The electric potential energy decreased because the electric force did positive work. And that minus sign sitting in front of the work done by the electric force says if the electric force does positive work, then the change in the electric potential energy will be negative. It decreases. On the other hand, the situation where we took those same 2 positively charged particles and now moved them closer together. Obviously, the electric force didn't want that to happen. The reason they moved closer together is because we moved them. So there was some external agent that forced them to come closer together by doing positive work against the electric force. So how the electric potential energy is changing is either going to be because the electric force does positive work when you let the system go, and the potential energy decreases. Or some external agent, i.e. you, has to do the positive work to get the electric potential energy to increase.